So for our first question, we're going to calculate the amount of heat required to raise the temperature. So this one is just our Q is equal to MC delta T. So we're just going to say that Q is equal to MC and our change in temperature. We're changing it from 10 degrees to 50 degrees. So therefore, we're going to have a change of 40 degrees Celsius. 40 degrees Celsius is the same as 40 degrees change in Kelvin. So we don't need to do any unit change in that regard. So we can just plug our number straight in. We're going to get our 0.1 times by our 4.18 times by our 40 Kelvin, or 40 degrees Celsius, and that should give us our 16.7 kilojoules. It is important to make sure that you are looking at the units here. This one says it's kilojoules per kilogram per Kelvin. So we need to make sure that our answer matches that. We're giving it our constant in kilojoules, so that means that our final answer is also going to be in kilojoules. It can be in joules, and it can also be in kilojoules. It could be in megajoules. So be aware, keep track of your constant there so that you can actually be aware of what's going on. Next question, we want to use our Q is equal to MC delta T again. So Q is equal to MC, but in this situation we're after a change in temperature, which was initially at 20 degrees. So we're going to say that T final minus our T initial. We're going to solve for our T final, so that means our T final is going to be equal to our Q on MC plus our T initial, which is then going to get us our 275 divided by our 0.2 times by 900 plus our 20 degrees, which should come out as being 21.5 degrees Celsius. Remember, it is also the same scale. So because we're keeping everything in degrees Celsius, if we just found 275 divided by 0.2 times 900, so this part here, if we just solved that part there, we would end up with hopefully a value of around 1.5. So when we add our 1.5 to our 20, therefore we get our final answer. For our final question, we're going to determine our specific heat capacity. So this one is going to be our change in Q is going to be equal to MC and our change in temperature. We're solving for our specific heat capacity. So our specific heat capacity is then going to be our change in Q divided by our M delta T, which is then going to be equal to our 375 divided by 0.5, and we caused a rise in temperature. So this is actually our temperature change. So this is going to be our 37.5 here, which should come out as being 20 kilojoules, kilograms per Kelvin or degrees Celsius. Either way, in that regard, doesn't really matter. With our next set of questions, we're introducing the idea of latent heat and using that one. So we are just determining the amount of heat required to melt the ice. So our Q is then going to be equal to MLF. We're just going to have 0.45 times by our latent heat of fusion, so 334, which is then going to be equal to our 150 kilojoules. Determine the amount of water at 20 degrees Celsius required to melt 0.01 kilograms worth of ice at 0 degrees Celsius. So this is our first one where we're looking at a change or a transfer in energy. There's two different ways of doing this. So we could say that the change in Q is going to be equal to 0 because we're going to assume that there is going to be no energy lost from the system. So that means that we're going to have our change in Q from the water, and we're going to have our change in Q for the ice. So as there's no loss of energy, we can now solve for this so that we're going to have the Q of the water as a negative is going to be equal to whatever energy gained by the ice. So we're going to have minus our MC of water times by a change in temperature is going to be equal to our mass of ice, mass of water, times by its latent heat of fusion. We're determining the mass of water involved. So we're after the mass of water. So we can say that we're going to have the mass of water is going to be equal to our mass of ice times by the latent heat of fusion of ice divided by our specific heat capacity of water times by our change in temperature of the water and minus there. Something to be aware of is that we've got 20-degree water. If we just need to melt the ice, we're not after a change in temperature of the ice. So that means that the ice is going to become water at 0 degrees Celsius. So therefore there is no delta Q involved in that. But what does that mean that our final temperature of the water is going to be? Well, that's going to be at 0 degrees Celsius then. So we end up losing, or the hot water, which becomes cooler and becomes cold water at 0 degrees Celsius by melting all of the ice. So that means that we can now plug in our values. So we get our ice, which is going to be 0.01 times by 334, divided by negative the 4.18 for water, times by the change in temperature of water. So our final temperature is actually 0. And our initial temperature is 20 degrees. Can anyone see a problem here? Some people will find this going wrong, mainly because we've got the negative here. This actually cancels out the negative down below. So we end up with a positive value because we're minusing our initial temperature, but then we're applying a negative to the whole thing because it's losing that temperature there. This one should come out to be a very nice small amount. So it's just 0.03995 kilograms. Another way of doing this would be to find the delta change of ice first. So we would find delta Q of the ice, and we would say that that would be the amount of energy that the water would give up. So we would assign them equal to each other, and we would find that delta Q there from the ice would apply that and make that equal to the delta Q of the water and find out the mass involved from that there. Both of those ways are completely valid of doing it. In our final one, we've got equal quantities of ice and water at 100 degrees Celsius for the water and minus 10 degrees for the ice. So we've got multiple different stages that are happening here. How am I going to do it this time? I'm going to do it the other way. So in this situation, I'm going to make the assumption that the hot water is going to give up its thermal energy to the ice. So I'm going to say minus my mass of water, C of water, and a change of temperature, which I'm going to actually write out as T final minus T initial of water. Wow, so many subscripts. I'm then going to say, well, that's going to be equal to, well, what are the stages the ice is going to go through? Well, first of all, it's going to be in an ice, and it needs to raise its temperature from minus 10 degrees Celsius to 0 degrees Celsius. So I'm going to have the C of ice times by the mass of ice, change in temperature of the ice, plus the mass of the ice as it melts. It needs to go through a latent heat of fusion, so therefore the ice is melting. And finally, once it becomes water, is at a lower temperature than the hot water around it, so therefore it will absorb the remaining amount of energy from the water and reach an equilibrium with the actual water there. So this is the mass of ice times by the specific heat capacity of the water. Mainly because once ice melts, it becomes water, and it will also reach its final temperature as well. So it's going to go from TF minus my T initial of ice. I'm going to simplify this. The mass of the water is going to be equal to the mass of the ice. So therefore, all my masses are going to cancel. My change of temperature of the ice is going to be equal to, well, it starts off at negative 10 and it goes to 0. So it's going to be final, which is 0, minus my initial, which is negative 10, which just becomes 10. and I'm going to expand out the first part, my CW, my specific heat capacity of water, times by my temperature final, that's negative, plus my specific heat capacity of water times by the temperature initial, which is then going to be equal to the specific heat capacity of ice, and I'm going to times that through by 10, plus the latent heat of fusion, plus, I'm going to expand this one out again, the C of water, which was originally ice, times by its temperature final, minus the specific heat capacity of water, but the initial temperature of the water after it's been transformed into ice is actually 0 degrees Celsius, so that whole thing is just going to be equal to 0 and we can ignore it. We're after the final temperature, so we've got that on both sides of it, so it's over here and over here. So we need to simplify that. So I'm going to say that this is going to be minus 2CWTF is equal to my 10 specific heat capacity of ice plus the latent heat of fusion minus the specific heat capacity of water times by the initial temperature of the ice. Finally, I can solve for the final temperature, which is then going to be equal to what we have before, plus the latent heat of fusion minus the specific heat capacity of water times by its initial temperature, divided through by minus our 2 specific heat capacity of water. Once we plug all of those numbers in, we should end up with a temperature of the system once it really reaches equilibrium of 7.54 degrees Celsius.